Now let's take a look at parallel resistors. In the circuit that I have drawn here, or the portion thereof, now let's look at parallel resistors. In the circuit that I have here, or the portion thereof, I have two resistors. We'll label this one R1 and this one R2. There is current flowing through. We'll label this I1. This will be I2, and this will be I3. Let's also stick some points on here so that we can refer to them. Make this one C, D, E, F, G, and H. So we learned before that the electric potential on the left side of the circuit, so at points C, E, and F, will have to be equal. And then same for the right side. This is because between these points it's just the wire, and the potential on an equipotential surface has to always be the same. So using this, we can then take a look at the potential difference over resistor 1. The potential difference over resistor 2. And we notice that these have to be equal to each other. Because the potential at point E and the potential at point F are equal to each other, the potential at point G and the potential at point H are equal to each other. So that means the differences also have to be equal. Now we also have some junctions in this, so we'll take a look at the junction rule. And that is that the current going in has to equal the current going out. So the current going into my circuit, or this portion thereof, at point C, then splits into current 2, I2, going through E and G, and current 3, I3, going through F and H. By the time it gets back to point D, it'll be back to being the same as I1. So now we can go through and look at what how the current, potential difference, and resistance relates to each other at each one of these resistors. So the current going through resistor 2, we've denoted as I2. The potential difference at resistor 1 is delta V sub 1, and my resistance is 1. We'll do the same thing for the other resistor. We have I3 as our current going through the second resistor. The potential difference divided by the resistance. Now, the total current that we have coming in, I sub 1, is going to be equal to the potential difference between before the junctions. It's also equal to the difference over each of the resistors, but we'll get to that in just a moment. So what we want to do is trying to find what equivalent resistance we could use that would end up creating the same amount of current. And again, this current is going to be equal to the sum of the currents going through the two parallel wires. So, plugging in for the two different currents, again, my current I sub 2 for the resistor 1 was equal to the potential difference over that resistor divided by the resistance itself, and same for resistor 2. Now we already said that these potentials were all equal to each other. So I'll go ahead and replace them in my equation here. And I'll see that they all cancel. So the equation for my equivalent resistance in a parallel circuit is going to be the sum of the inverses. So this could be written a few different ways. You can keep them all in fractional form. Or you can write it using exponents. Either one is appropriate, but again, this is for resistors in parallel.